So the next talk will be given by Professor Suvankar Chakraverty from IISc Mohali.
Good morning and thank you Srimanta, Priya and Arindam and other organizers for giving this opportunity to discuss about our recent results. And no, this is a blank slide. Okay. So I'm not sure what wrong I did with them that they have given me the talk after D.D. Sharma. It's very difficult, right? And Amit is so happy that people will now understand the difference between the good and bad talk. But what is done is cannot be undone. So let me start talking about what we are doing. We are working on kind of topological aspect of matter. And recently, while having a dinner with my family, I find this, so since we have some foreign delegates, it's kind of mandatory to tell about my institution. I'm coming from an institute called Institute of Nanoscience and Technology, which is located at the northern part of India, which is kind of around 2,500 kilometers away from this place. And this is under the Department of Science and Technology and the first institution which is dedicated to the nanoscience and technology. So this is the thing which I have seen. It calls hum nahi sudhrenge. It means will not change. That is the idea of a topology, right? You cannot break the topology and it is always protected by its topological structure. So while I got the invitation, so it was the first I prepared this title, the Spin-Polarization and Topological Hall Effect in Oxide Interfaces and Thin Film. So topology plays a very important role in quantum mechanics, and the reflection of this topological protection and other in the measurable quantities that we are looking into. But when I got the schedule, it seems like instead of 30 minutes, which we are used to, it is a 45-minute talk. So it has been now changed to a more general one, topological effect in oxide interface and thin films. So this is the kind of slide which actually represents the overall idea of our work. And many of you have seen this slide. It says that if you have a conducting material or the electron or the conducting particles are moving under the influence of an electric field, then what happens? The momentum and the spin, they locked with each other. But now we ask the question, in addition to this, if you have a non-trivial spin texture, either in the real space or in the K space, then what happens? So we are going to show that if the spin texture is in the real space, then it is well known that the signature in Hall or the transverse resistance, it gives rise to some kind of signature known as topological Hall effect. But if the spin texture is in the momentum space instead of a real space, then the signature in the longitudinal resistance comes, that is in the magnetoresistance. So we have a list of lot of collaborators. So these are the list of the collaborators with whom the paper has been published. So we have several, including there are many who are sitting here. The work has mainly been done by my student Nand Kumar, who is at now this University of Nepali, and with Anamika, who is at MPI, and Ruchi and Neha. And recent work has been done by Vivek, who is here, and Harsha. So these are the list of the theory people who has contributed to our work. Yeah, Amit, yeah. So this is on the 1st of January. So we don't know if it is our data effect or the 31st December effect. Okay. So this is the outline of the talk. So we're first going to talk about growing of oxide film using pulse laser deposition system, which DD has already given a nice introduction about how this interfaces and this material could be possibly become conducting. So we're going to talk about two materials, and we are talking about the effect of the laser fluence on your target and how it changes the behavior of the material. First system we're going to talk about is lanthanum vanadate, strontium titanate interface. Second is strontium iron molybdenum oxide, double peroxide thin film. Then second, we are going to talk about some unusual quantum oscillation in resistance, and we presume that it's showing some signature of non-trivial spin texture in momentum space, and material used is lanthanum vanadate and potassium tantalate. Then finally, if time permits, we'll talk about some ongoing work on lanthanum iron. This is published, lanthanum iron oxide strontium titanate interface, and tungsten dope SFMO. And so these are the paper related to this. For this part, we have few more and we're struggling to publish. And this is, as I said, the last part. the work is under progress. Okay, so this is for my student friends to motivate why PLD and how PLD can be used and why it could be useful. So this is a schematic of a PLD pulse laser diffusion system. You have a target here and you shine an excimal laser on this, and from the target, the particles comes out and you have substrate here, and it kind of goes and stay on the top of the surface of the substrate, and the films or the interfaces are formed. And this system is typically equipped with a very fine, nice technique called reflection high energy electron diffraction system, by which you see some oscillation in the diffraction pattern, and with the growing of the thin film and counting this number of oscillation, basically you can talk about how many number of monolayer precisely have grown on the top of this film. So advantages, you can have epitextual growth, you can use the growth kinetics as well as dynamics, thermodynamics of the system. So actually you can grow this kind of extremely high quality thin film. This is a TM image of our sample. And actually while growing the sample, you can use the thermodynamics, where you can use what is known as the Ellingham diagram. For example, if you want to grow iron at 3+ state, then you should try to come here, because if you grow here or here, there is a possibility. So this is the temperature, 1 over temperature, and this is the oxygen partial pressure in logarithmic scale. So if you grow here, there is a possibility that you can heat the iron at 3+ state. Of course, there is some deviation there. And there is something called kinetics, because it depends on what is the energy of the laser you are using on the top of your target. But by depending on this, the kinetic energy of the ablated species changes, and this gives the kinetics of your film growth. So this is a very simple idea of general formula of this perovskite oxide. This is AbO3 with a very simple structure of a cubic structure, where A site is sitting at the center of the cube, B sites are occupying the corner of the cube and surrounded by oxygen atoms. Why this kind of perovskite material is interesting? If you think of any interesting physical property, superconductivity, magnetism, ferroelectricity, and so on, and the connection between them, that is the coexistence of them, you can find is this kind of material. So the first story of this conducting interface of this perovskite oxide started with lanthanum aluminate and strontium titanate heterostructure, where both are high bandgap material, but the interface become conducting when you juxtapose one on the top of other. And this is the resistivity data as a function of temperature. It goes down with decreasing temperature. This is a work done by Otomo and Harold. So this slide might look a little bit busy slide, but when you talk about a two-dimensional electron gas system, what is the parameter you look into? You look into what is known as the mobility of the charge carrier. So initially the system where people have seen this conductivity around 80s or 90s is gallium arsenide-based system, and people have seen this is the year and this is the mobility. People have observed quantum Hall effect and fractional quantum Hall effect. For both of them, people got Nobel Prize. But there is a scenario change around 2002 when people have seen this kind of appearance of conducting interface in oxide material, namely lanthanum aluminate, strontium titanate. Then around 2020 onwards, people have started seeing there is a jump from strontium titanate based system to a potassium tantalate based system. Why it is so? Because in potassium tantalate, the spin orbit coupling strength is almost 1 order of magnitude higher. So you can see the effect of spin orbit coupling in the system if you can make an interface and if you can get conductivity at the interface of the system. So after that, if time permits, we'll talk about the revisited of strontium titanate system, where we have seen some very interesting physical properties. So when we talk about this kind of interfacial conductivity in a perovskite based material, there are 4 possible scenarios. One is oxygen vacancy, cation intermixing, polar catastrophe, and band alignment. We ask the question, what is the effect of film stoichiometry? So you have AbO3 deposited on A prime B prime O3. So what happens if you change the ratio of AB stoichiometry? So to understand this simple structure, which Didi has already talked about, to understand the idea of this polar catastrophe, one can categorize this perovskite oxide into two types. One is non-polar and another is polar. So if you take a strontium titanate and look into each layer, this layer is titanium 4, oxygen -4. So this is charge neutral, and this is SRO +2 -2, so this is also charge neutral. So this is known as a non-polar material. On the other hand, if you think about lanthanum aluminum oxide, then this layer has a -1 charge and this layer has a +1 charge. So it is kind of alternating plus minus, but overall it's a charge neutral material. So if you think of this charge at each layer, so if you take a non-polar material as a substrate and start growing polar material on the top of that, then you have -1 +1 -1 +1, and this gives rise to an electric field like this. And when you convert this electric field to a potential, it gives rise to a diverging potential. So as you start growing the material and material thicker and thicker, this potential start diverging, and nature doesn't like this diverging potential. What it does, people believe that it sends half of an electron from the top surface to the interface. And this gives rise to a non-diverging potential. And that is, people believe that this is the origin of what is known as polar catastrophe scenario. So what will be the signature of that? The system should be half electron doped per unit cell, and a critical thickness of this film is required to get this material, this interface conducting. So this is the paper we are going to talk about. So I have already given this, there is no need. This is the pulse laser deposition system we are using. So what we are doing is the following. We are preparing lanthanum vanadium oxide on the top of strontium titanate, and it has a lattice mismatch less than 0.4%. And why it is taking that less possibility of this oxygen vacancy in the system, because vanadium is not as bad as aluminum, and the growth condition is much milder than lanthanum aluminate. So this is the laser spot on the top of a target, actual laser spot. So we define this laser fluence as laser energy per unit area on the target. So if you measure the energy, if you take this area of the laser spot, then you can actually calculate what is the laser fluence on your target. So what we have done is the following. We prepared sample of lanthanum vanadate on the top of strontium titanate and looking into the interface, and we prepared the sample by using various amount of laser fluence starting from 0.6 and goes up to 4 joule per centimeter square. And you can see when the laser fluence is small, below 1.1 joule per centimeter square, it is insulating in nature, that with decreasing temperature, the resistance increases. But when it is higher than 1.1, that is 1.2 onwards, it becomes conducting, and it has a it doesn't change much with increasing fluence. So then we started calculating what is happening. So if you plot the laser fluence as a function of the ratio of lanthanum and vanadium, you can see this area is the lanthanum rich area, and this is lanthanum deficient area. And in the lanthanum deficient area, you get the conducting nature, and lanthanum rich area, you see a insulating nature. So this is already people had seen this similar thing in lanthanum LAOSTO system. So this dotted line is, yeah, please.
So how did you choose the frequency of the laser in those measurements? Like, how did you select that?
We have just taken 4 Hertz frequency. That's it. We never changed the frequency.
Yeah, but how did you choose that specific frequency? Like, why did you want to study the transport at that frequency as a function of fluence rather than other frequencies?
No, by frequency, what do you mean? The repetition rate or the laser energy?
The laser frequency, right?
Frequency of the laser light?
Yes.
Shined on the top of this ablation. That is, we didn't choose. We bought the one which has kind of 250 nanometer wavelength. That's it. This is excimer laser. This is not a tunable laser. This is a fixed laser.
Okay, so that was just what you had? So
Yes. So if you see this has a remarkable correspondence with people had seen for LAOSTO system and our deposited LVOSTO system, that if you have a strontium lanthanum deficient material, it becomes conducting, but when it is become lanthanum rich material, it becomes insulating. So what about the other mechanism? For example, oxygen vacancy. We have annealed the system and we have seen there is no change, and cation intermixing is that there is no critical thickness in the film is needed, and for polar catastrophe, what we need is a need of critical thickness. So what we have done is the following. to check this, we have taken 2 joule per centimeter square, which is above the critical energy of this laser fluence, and we started growing different number of monolayers of lanthanum vanadate on the top of strontium titanate. And what we have seen, even if you choose above the critical energy of the this laser fluence, but below 4 monolayer, this system remains insulating. Above this critical thickness, it becomes conducting, and if you can see, this is approximately 3 into 10 to the power 14, which is kind of half electron dope per unit cell. So what we conclude is the following: both A-side deficient film and the critical thickness of the film is needed to realize the conducting interface of 2 insulating perovskite oxide. So we believe that A-side deficient film triggers the polar catastrophe. That is what we believe. We don't know if it is true or not, if there could be something more, because as Tanuja was mentioning, for gadolinium titanate, people could see this for 1 monolayer of thin film only. Okay, now we are going to, in the second part, which is the non-trivial spin texture in momentum space, and we're going to talk about lanthanum vanadate potassium tantalate interface and looking into the longitudinal conductivity. So if you have a non-trivial skyrmionic spin texture in real space, and if you send an electron through this, what happens is the following: if you take a normal material and if you look into the Hall measurement, then if you have no magnetization in the system, then the normal Hall is coming from Lorentz force, and it is simply proportional to the applied magnetic field. And if you have a magnetic system typically, then in addition to that, you have a term which is proportional to the magnetization of the system. But if you have a system with non-trivial magnetic spin texture, then in addition to these two, you see another term which coming from the Berry phase idea and giving rise to something called B effective, coming from the idea of the Berry phase. This is a pseudo-magnetic field, and it gives rise to something very weird in the system and is known as the topological Hall effect, coming from the Berry phase in the real space. But here you are looking not into the longitudinal resistance, but you are looking into the transverse resistance under the application of a magnetic field, which is the normal Hall. But what if there is a non-trivial spin texture in the momentum space instead of real space? So possible non-trivial spin texture in momentum space is a Rashba system. And what is that Rashba system? For a free electron, the Hamiltonian is p square by 2m, and energy is proportional to the k square, and it's a simple parabola. So now if you think that you are having an electron moving with a relativistic velocity under the application of electric field, then in the rest frame of the electron, this electric field is now converted into the magnetic field because of the Lorentz transformation, and now your spin is kind of fixed in along this direction. Now quantized in this direction. Now if you inverse the direction of your motion, then the direction of this quantization changes, and this gives rise to the spin momentum locking, and this is known as the Rashba effect. And now your energy is no longer a k square like, it has a k square plus minus k dependence, and your one parabola is now split into two parabolas, and instead of having one Fermi circle, you have two Fermi circle with spins rotating opposite to each other, giving rise to an idea of spin chirality in the system. So possible perovskite oxide which can have a very strong spin orbit coupling is potassium tantalate. In compared to strontium titanate, it has a spin orbit coupling strength around 300 milli-electron volt, which is more than order of magnitude more than strontium titanate system. So these are the paper. I am not all going through. A few we are going to try to cover, which has been published very recently. So we have grown strontium lanthanum vanadate on the top of potassium tantalate. And we are showing the data of 4 monolayer lanthanum vanadate grown on potassium tantalate. So how do you judge the number of monolayer grown? We are judging the number of monolayer grown from this reflection electron, high energy electron diffraction system. You can see exactly 4 oscillations comes, and then we stop the growth. So it means you have 4 monolayer of lanthanum vanadate on potassium tantalate. And you can see that this material is conducting in nature, the interface is conducting in nature. The Hall is completely linear with a charge carrier density around 4 into 10 to the power 14 centimeters, 13 centimeters square. And we had calculated it has a very strong spin orbit coupling, and Rashba strength is around 4.4 Tesla, which is very this is the strongest possible reported for any oxide material. Let us think that if you apply a magnetic field and your electron is moving classically, then what happens? Because of the Lorentz force, it starts rotating in a circle. But classically, this orbital size is not quantized, number one. Number two, the energy are not quantized. But quantum mechanically, if you look into this, the orbital size is quantized by this quantization rule, and energies are also quantized by using the Landau level formation and the Landau quantization. Okay. So what you see, if you send the current, you apply the magnetic field and look into the longitudinal resistance, you see an oscillation in the magnetic field, because by changing the magnetic field, you are changing the distance between the Landau level, and when it crosses the Fermi level, it gives rise to the oscillation in the resistance in the longitudinal direction. This is known as quantum oscillation in the system. So if you can see this quantum oscillation or Shubnikov-Dahas oscillation in the system, you can talk about many things about your system. Number one, what is the shape of the Fermi surface? If it is two-dimensional or three-dimensional, because by rotating the material, you can get an idea if it is a two-dimensional Fermi surface or a three-dimensional Fermi surface. You can talk about the effective mass of the system, and you can talk about even what is the nature of the band, if it is a trivial or it is a non-trivial band. So this is the raw data of our quantum oscillation as a function of magnetic field. This is a magnetic resistance. When you subtract this background, you can see this kind of oscillation, which is not as good as if people see in the semiconductor material, but for an oxide material, believe me, it's not a very bad oscillation. There is something called Landau-Onsager equation, which is like, so this up point and down point, you can actually mark it as a Landau index, which is n. So if you mark this as a Landau index, then this Landau index is inversely proportional to the applied magnetic field. So if you plot this 1 over v versus n, it should be a straight line passing through the origin. But if in your system, this is for a material where you have a parabolic band. But instead of having a parabolic band, if you have a linear band crossing, where this linear band crossing, the crossing point gives the idea of a magnetic monopole at the momentum space, then in addition to this term, you must have a Berry phase term. Then this line or the Landau index plot should not go to the origin, but it should go to the 0.5, and this 0.5 will give rise to a pi Berry phase in the system, and that signifies that your band structure is a non-trivial band structure. But in both cases, this should be linear as a function of 1 over b. But recently a paper came which says if you have a non-trivial spin texture in K space, which Rashba might provide, then this Lipschitz-Onsager equation is now modified by a term which is C into B. This is C is a derivative of susceptibility, right? Derivative of susceptibility. And then if you plot this, this should not be linear in 1 over b. So when you plot our data, Landau index as a function of 1 over b, then it shows a completely nonlinear behavior, and this could only be fitted by using this formula. And this gamma is basically also gives you the idea of this, what is the Berry phase in terms of your electronic structure, and we found that we also have a Berry phase pi in the system. So there are 2 points. One, we have seen the appearance of a susceptibility, derivative of the susceptibility term in the system, and we have a non-trivial electronic band structure. So from this, what we are concluding is the unusual quantum oscillation in the resistant, non-trivial spin texture in momentum space possibly, and where it is reflected, in contrast to a topological Hall effect, it is reflected to a longitudinal resistivity. So now we are going into, since that there is, I have 10, 15 minutes, 14 minutes, okay. Then we are going into, again, revisiting this area of strontium titanate, and we are going to talk about the material of lanthanum iron oxide strontium titanate interface. And we are going to show something very interesting, which initially we could not understood why it happens. So this is the Reed oscillation. Reed oscillation means you are looking to how the sample is growing and what are the number of monolayer you are growing on the top of your film. We have grown around 6 monolayer of lanthanum iron oxide on strontium titanate. the interface is completely conducting, going down to around 2K. Now, this is the interesting point. So if you look at the magnetoresistance and Hall data, so this left-hand side corresponds to magnetoresistance, and this is the, right-hand side corresponds to the magnetoresistance, and left-hand side corresponds to the Hall. And this is the zero of this axis. You see a positive magnetoresistance. And it's a completely linear Hall. We fit a linear fitting, and it gives 0. The Hall, the extra part of the Hall, which could be an anomalous Hall, is 0. But when you go to 300 Kelvin, this magnetoresistance becomes negative magnetoresistance, which is typically we don't expect. Usually this negative magnetoresistance we observe at the lower temperature, and high temperature you see a positive magnetoresistance. And at the high temperature you see a non-linear Hall. And when you subtract this linear feed, you see this anomalous Hall part coming in the system. So we made a systematic temperature dependent measurement, and we can see that starting from 100 Kelvin to up to around 150 Kelvin or below, it is a positive magnetoresistance, and above that it is negative magnetoresistance. And this anomalous Hall also started from 100 Kelvin, above the 100 Kelvin, and it remains even up to room temperature. Okay? So this is a very sharp contrast from what you see in a normal half metallic type material. And this material being very transparent, this is the transparency. This is a you can call it a transparent spin polarized material. So initially we thought is the following, recalling a very old paper by Tokura on this LSMO, where what they said is the following. If you think of 3 spins in the real space which are canted to each other and localized, now if you send an electron starting from one point to other point, if it goes adiabatically and return back to its original position, then it gains a Berry phase. So what was the idea? Idea was this flask is proportional to the solid angle subtended by these 3 spins. So what we thought is that at the low temperature, the spins are parallel to each other, they are locked. But when you increase the temperature, there is because of the thermal fluctuation, the thermally stable state is a spin canted state. And because of this spin canting, this system is gaining some Berry phase, and that is giving rise to this negative magnetoresistance or anomalous Hall effect. But referee didn't like it. We are also not sure. So by taking, and fortunately the day we got the report, there was a conference at Pune last year and Priya was there. So Priya helped us with this band structure calculation. What's it kind of shown is the following. At high temperature, STO is at a cubic phase. And because of this cubic phase, this system is half metallic in nature. But once there is a transformation from cubic to a tetragonal state, it becomes a non-spin polarized material. So this is a very interesting thing. So this is a crystal driven half metallicity to non-half metallicity transformation. Okay, so the spin polarization, this interface to a non-spin polarization state by changing the crystal structure of this material. Then recently, not recently, but a few years back, we started working on strontium iron molybdenum oxide. Why we wanted to do this? As I have shown that we are working on this strong spin orbit coupling interface material. We want to see if you have a strong spin orbit coupling interface, conducting interface, and if you use one half metal as a spin injector, then what happens to the system? So one of the possible material was strontium iron molybdenum oxide. And this material was shown to be a very highly spin polarized material with a negative magnetoresistance, high negative magnetoresistance, around 31% at low temperature and 8% at room temperature. And this was done on single crystal material. But the problem was that when people started working on the thin film, people could never get more than 4 or 5% of this negative magnetoresistance. So we were looking into this literature and we could found that what people have done in terms of thin film growth, they have just used the Ellingham diagram and tried to grow the sample using different growth condition, that is the growth temperature and changing the oxygen partial pressure. Now, if we summarize all the so far measured data or the magnetoresistance data, these are all data from thin film. So see, it has never crossed 4 to 5% as a function of years. And whereas for the this is at room temperature. But for single crystal, it is around 10%. So we wanted to see if we can beat these numbers. So what we have done, as I said, that in pulse laser deposition, you have two knobs. One is thermodynamics and another is kinetics. So people have so far tried with the thermodynamics. We wanted to try with the kinetics. That is, change the laser fluence and see what happens. So we had changed the laser fluence and we used different laser fluence, and this is the resistivity as a function of temperature. And we have seen that if you change the laser fluence, there is an insulator to metal transition in the system. And this is the magnetoresistance. I'm not going to the XRD data. There is a crystallographic change in this. That will be evident from this next graph. So this is the magnetoresistance. And you can see at low temperature, we could get around 20%. And at room temperature, we could get around 6% of the magnetoresistance with changing the laser fluence, which is kind of almost double than what people had seen for all reported thin film. So by changing the laser fluence, what we are actually changing? We're changing the ratio of iron and molybdenum site. So it is seen that if you have a iron rich sample, then the system is metallic and you have a high magnetoresistance. Whereas exactly at 50-50 concentration or above that, it becomes insulating as well as the magnetoresistance decreases. And by changing this kinetic of the growth, we could go around 7 to 8% of the magnetoresistance data in our sample at room temperature, which is much above than what people have seen so far for a thin film system. So laser fluence can play a vital role for different physical properties. But SFMO has a problem. What is that? It decays very quickly. In a few days, it decays. So I was discussing with Didi about this. Didi said that there is a possibility you dope the system with tungsten, because tungsten doped SFMO is also a very interesting system, half metallic, and it has a very long lifetime. We started working on this and we found it is not only about how stable it is, it has a very rich phase diagram. Recently we made this phase diagram. So this is the concentration of molybdenum doped in tungsten. So if it is a SFMO, this is a conducting, so half metallic and ferrimagnetic or ferromagnetic material. But if you go towards the iron tungsten side, it is an antiferromagnetic insulator. And there was a lot of debate about this origin of this metal insular transition, and Didi has a paper in 2000, I believe, that it shows that there are two possibilities, that there is a valency fluctuation in addition to the percolation threshold, which gives rise to this metal insular transition. But there are many surprising things. In Didi's paper, I could see that in resistivity versus temperature data, below 50K, you didn't show the data. I asked you, you said that it was going up very fast. And okay, and also when I look into the Tokura data, I could actually found that below 50 Kelvin, it is going up very rapidly. So this is the XRD data, and this is the resistance data of 30% tungsten dope, 30% molybdenum dope, iron tungsten oxide. So you see the resistance, there is a fast resistance metal insulator transition around 200 Kelvin, and there is another metal insulator transition around 50 Kelvin. When we look into the magnetization data as a function of temperature, there is a cusp-like structure which kind of signify an antiferromagnetic transition, and then there is another ferromagnetic-like structure which we don't know yet. So these are all just, we got the result just last month or so, and these two correspond very well with your resistivity data. Then we look into the magnetoresistance data. So at low temperature, it has a negative magnetoresistance with around 40% magnetoresistance. But as we increase the temperature around 30 Kelvin, there is a transformation from negative magnetoresistance to a positive magnetoresistance. So this is happening exactly at this position, this positive to negative magnetic-resistance transformation. And again, at higher temperature, there is a transformation from positive to negative magnetic-resistance. And you see, this is the Hall data. At very low temperature, we tried to fit with anomalous Hall formula, but it doesn't fit, and it gives rise to some additional Hall data, which is kind of seems to us like a topological Hall, but we are not sure about the origin of this extra Hall term. So if we summarize all this data, so this is temperature versus resistance, this is temperature versus magnetoresistance. You see where this transition in resistance happens, you see the transition in the magnetoresistance. And at this low temperature, there is something like topological Hall effect coming, and at this point, this anomalous part of the magnetoresistance also vanishes. But the important part is that even if at room temperature there is no anomalous Hall effect, but you still have a negative magnetoresistance. So we don't understand anything, but we are free to discuss. If you have any question, please ask. So these are the conclusion. First, we show the strength of a laser pulse laser deposition system, where you can change the laser fluence and you can vary the stoichiometry of the material and can see very interesting properties. And if you then second part, we have shown if you have some non-trivial spin texture possible in the momentum space, then that should be reflected in a longitudinal conductivity as a non-linear Landau-Fan diagram. And third is the unusual magnetotransport, negative magnetoresistance, anomalous Hall effect, and topological Hall effect. And we are working on this thing. So thank you very much. So these are the few publications related to this. If you have any question, please feel free to ask.
So the room is open for questions. Dhavala?
Just wondering if you have seen any response to in-plane magnetic field in these samples where you see negative magnetoresistance. The reason being spin textures can be captured quite a lot by planar Hall effect or so?
Yeah, so you're talking about tungsten drop.
Yeah.
Have we measured? Not yet, no? In plane we have not measured yet, because this is the sample prepared 2 months back. So we have not done yet.
Just wondering, you are using like lanthanum deficit or lanthanum reach, iron deficit, iron reach. Then of course all the concept of the nominal valence, etc. are different, and your polar catastrophe, exactly the way you have started with, they are different. And I don't know, under this condition, is there also influence on the oxygen vacancies being created if you make more lanthanum?
So Tanushree, what we have done to get rid of this question of oxygen vacancy, we took the substrate, we masked it half. We grow the sample on the one side and keep the substrate at the same growth condition, because this oxygen vacancy basically comes from the low oxygen pressure in the chamber and high temperature. Then we measured the resistivity at both parts. This masked part is always insulating. So at least detectable oxygen vacancy we have never found in terms of transport measurement.
But in terms of the balance of the transition metal, of course it takes transition metal or any metal,
Right.
like whatever it all gets changed. So
Yes.
physics must be
Definitely. Because, and Tanushree, you can see that you need a very small deviation from the 50-50, kind of 0.1% deviation from the 50-50 gives rise to the conducting state. If you, it's a very sharp, almost, yeah. So this is insulating and this becomes conducting. This is just the 50-50. So we don't know how this band structure or what it looks like.
Same question, but slightly differently. Cation deficiency would inevitably mean you're doping the system.
Cation deficiency in the film.
Yeah.
But if you see on the film measurement, it is not conducting. Only if you wire bond and go at the interface, it is conducting. You take the sample, you grow a thin film, the thick film, then you just put some wire with silver paste, it is not conducting.
I understand, but the question is, one would like to know the fate of those doped charge carriers.
Yes.
If you have cation vacancy, that and if it is not compensated by oxygen vacancy, then you have doped charges.
Yes.
The question is, what happens to them where they are? I think
Yeah,
that is the
I
essence of
understand.
the question.
Yeah.
And the other is just a comment, maybe because you asked me about the conductivity. you can look at Sugato's thesis. The phase diagram that you're talking about, tungsten, he had worked out for the bulk material in
Yes,
detail.
yes, yes.
And there are some mixed phase systems where it tends to form nanoclusters of one in
Yes,
another.
yes.
So
I think that is there on your 2000 paper also. Partially,
at least most of the results you'll find
Sure.
also in his thesis because it's available. It's
Sure.
in public domain.
Sure.
So just have a look.
Sure.
Suvankar, very good talk. I just want to look into this, your LAFeO3 part, the very unusual transport that you saw, because as I know, LAFeO3 shows a very complex magnetism.
Yes.
So did you take into, do you have a LAFeO3 magnetism data? I mean, how did you consider that?
We have measured MH and MT, but we didn't see anything surprisingly strange between 5K to 300 Kelvin. I can show you the data. This is there in the supplementary of this paper. Everything is there, but I understand your point, but we didn't see anything very strange in this magnetization data. At least you can see this paper. It is there, but we'll discuss. Definitely, yeah.
So one small question.
Please.
So where you are comparing the fluence in that slide, so what about the film thickness? Are the film thickness same for all the samples?
We keep the film thickness same by changing the deposition time.
Deposition.
Deposition time. And that paper also we have shown the read. We could see the read for almost all, and it was very easy for us to judge how many thickness. Of course, there is a plus minus few nanometer difference.
Do you see some effect which could not only be attributed to a heating effect from the fluence? I mean, is that an interpretation, or is there something beyond that?
Yeah, I understand your point. The point is that we also thought, but that we have no control. When you change the laser fluence, the kinetic energy of this material changes. And so there is a possibility of inverse sputtering from the target substrate as well. And that can also heat up the target also, but these we don't have any control over. I understand your point, yes, definitely.
So I have a short question. Like, you analyze the Shubnikov-Diaz oscillation data at very high magnetic field because you have a very disordered sample compared to the low mobility sample compared to the semiconductor.
Much low.
So how good it is analyzed? Typically, Shubnikov-Diaz data is analyzed at low magnetic field.
Yes.
This oscillation, how accurate it is, this analysis?
Although it is, because once it is non-linear, then you cannot actually index this.
Yeah, also your peak was quite broad, right?
Yes, but we have a data until 60 Tesla also, which I didn't perform, so I didn't want to show. That data exactly match with this low field data. So that gives us an additional confidence that is not that bad data.
Okay.
So 60 data, I'll show you the 60 Tesla data, and that is kind of very much correspond with this data.
And another thing, can these samples be gated?
Yes, this is very much gated because K2 has a very high dielectric constant, but you cannot get top gate, you have to get bottom gate.
Okay. If there is no more questions, let's thank the speaker again.
Yes, thank you.